A horse and cart sets off down a completely straight track at a speed of 3 kilometers an hour. At exactly the same time, 6 kilometers down the road, another horse and cart sets off, heading directly towards the first horse and cart, also at 3 kilometers an hour. It's a cart crash waiting to happen. At the beginning, a small fly takes off from the nose of the first horse and flies in a straight line at a speed of 6 kilometers an hour toward the nose of the second horse. As soon as it reaches the nose of the second horse, it turns around and flies directly back to the nose of the first horse at a speed of 6 kilometers an hour. When it reaches the nose of the first horse again, it turns round and heads back to the second horse, and so on. The pattern is repeated until sometime later the horses collide and squash the fly between their noses. How far did the fly travel from the first takeoff to the squash incident? Now, this is a problem set in Math World, a slightly strange place in a nearby parallel universe where things work subtly differently than here on Earth. Every math classroom or exam hall doorway is a portal to Math World, as is any piece of paper or screen showing or explaining such a problem. You're expected to use the numbers given as an approximate, simple model of a real-world situation. But before we go any further, let's state a few assumptions that we'd need to make in order to get the answer that the person who set the problem is really looking for. Assumption number 1. The horses and carts are travelling along a completely straight track. This sounds pretty simple, but there are a couple of possibilities for what is actually going on. Remember, they're travelling on the surface of the Earth, which is an oblate spheroid with a circumference of between 40,008 kilometres pole to pole and 40,075 kilometres around the equator. Of course, they could be travelling east to west or west to east along a line of latitude, which could result in a much smaller radius, depending on how far north or south of the equator they are. Let's assume they're travelling around the equator, and we'll assume a perfectly circular shape, ignoring any of the lumps and bumps and distortions of the Earth's surface. If we assume they're travelling along a 6-kilometre arc around the Earth, then the fly will be travelling maybe 2 metres off the ground, so we'll be travelling on an arc with a slightly larger radius from the centre of the Earth than that of the ground. It turns out that the starting points will be nearly 1.9 millimetres further apart at a height of 2 metres than on the ground. This is negligible over a distance of 6 kilometres, especially when you consider how difficult it would be to measure the distance between the horses' noses when they keep moving their heads anyway. We'll ignore it. Alternatively, maybe someone has dug out a genuinely level 6-kilometre track through the Earth's crust. If that's the case, then we can see that the cutting would have a depth of about 70.5 centimetres at its deepest point, which is a relatively minor undertaking in terms of global engineering projects, but it does require work over a 6-kilometre stretch of road just for a little mathematical puzzle, so it probably wouldn't attract the necessary funding. On balance then, it's okay to operate on a flat Earth basis and assume that we have a straight, level 6-kilometre road. Assumption number 2. The horses and carts travel at 3 kilometers an hour. This sounds reasonable. It could mean that they travel at a constant 3 kilometers an hour, or it could mean that they travel at an average of 3 kilometers an hour. They're going to be travelling for an hour before they collide in the middle, so if the 3 kilometers an hour is an average speed, any small fluctuations along the way won't make any difference to the end result, although they could make a huge difference to how you're able to calculate the answer. It's worth just stating for the record that horses in Math World don't slow down slightly to let out waste products and exhaust gases in the way that real-world horses do, so they're able to maintain a constant speed. If the speed is a constant 3 kilometers an hour and the horses started from rest, then it would be a little bit concerning that they were able to instantaneously jerk from rest to 3 kilometers an hour. This change in velocity in zero time implies infinite acceleration, which, under Newton's second law, the acceleration of an object is dependent upon its mass and the magnitude of an unbalanced external force acting upon it, causes some issues. Newton's second law, or N2 as it's known to its friends, tells us that the force is equal to the mass times the acceleration. If we say that a horse, small cart and driver has a mass of around 1,000 kilograms, then the forces involved in accelerating this mass instantaneously to 3 kilometers an hour are essentially infinite, and certainly very damaging to the horse, cart and driver. It'd be more realistic to arrange the situation so that the horses and carts start a little over 6 kilometers apart, gently accelerate to a constant 3 kilometers an hour, and when they're exactly 6 kilometers apart, the fly could set off from the first nose to the other nose. This would take very careful coordination and planning, but it's more feasible than expecting instantaneous achievement of 3 kilometers an hour for each horse and cart. For example, someone could stand at the halfway mark and start waving a large flag to signal the start time. The light from the flag would take the same time to reach each cart driver, so they'd start moving at the same time, assuming they've got the same reaction times. The horses would start some distance behind their official starting position, 6 kilometres apart, and gently accelerate at the same rate in a well-rehearsed routine to 3 kilometres an hour. And we'll also need to assume that the cart drivers are able to judge speed with great accuracy and control the horses to maintain that exact speed. Assumption number 3. The fly travels at a constant 6 kilometres an hour backwards and forwards between the noses of the horses. If we weren't operating in math world, there would be a few issues with this aspect of the problem. Firstly, we'd have to train the fly to set off at exactly the right time. This would either be after the infinite force trauma of instantaneously achieving a speed of 3 kilometres an hour on the first horse's nose, or the fly would need to be capable of judging exactly the right time to set off as the horse whose nose it was sitting on passed the start line. We'd also have to train the fly to fly backwards and forwards between the two horses' noses, and hope that neither horse breathes in too deeply at an inopportune moment, sniffing up the unfortunate insect to a quite unpleasant mucus-based death up a horse's nostril. We'd have to carry out the training without letting slip that the poor fly would be facing certain death at the end of the exercise anyway, and hope that its powers of deduction weren't sufficiently well developed that it would anticipate that the time interval between turnarounds was getting smaller and smaller, and at some point there was going to be a coming together moment which would not end profitably for the fly. I don't know if you've ever watched a fly, but travelling in a long straight line doesn't come naturally to them. They dart around all over the place in seemingly random directions, so the whole straight line from nose to nose piece would need to form a significant part of their training. I once spent a couple of hours watching a fly dart around my room when I should have been doing some homework. It seemed to have an almost inexhaustible appetite for randomly zipping in different directions over short bursts. I didn't manage to discern what its objectives were, but it never managed to fly in a straight line for more than a metre or two. This little study episode ended with a power cut and the lights went out, plunging us into total darkness. The fly was mid-flight when this happened, and I was very concerned for its welfare, suddenly finding itself flying around without any light, not knowing how or where to land. I listened carefully to see if it bumped into anything, but I never heard it, and I never found out what happened to it next. As for flying at a constant 6 kilometres an hour, this may be an even greater challenge. How would it be able to tell that it was travelling at the correct speed? It would be too small to carry a GPS device, and certainly not skilled in reading and acting upon such a thing, even if we did have a sufficiently miniaturised piece of equipment. Then there's the problem of wind. If the fly maintains a constant airspeed, any slight gusts or breeze would mean that its speed relative to the ground would vary. Overcoming this becomes even more complicated if the wind is blowing at an angle to the road, as the fly will have to carefully judge the forward and sideways components of its speed in order to fly exactly along the straight road at 6 kilometres an hour. Tricky. Another issue is the instantaneous acceleration from rest to 6 kilometres an hour at the start, and the instantaneous turnaround every time the fly reaches a horse's nose. We've already seen that such magical instant changes of velocity don't happen in the real world, so we'll just make an assumption that the acceleration and deceleration phases are exactly balanced by slight changes to the fly's speed in flight to make sure that its overall average speed is 6 kilometres an hour. Lastly, in math world, we're able to ignore the fact that 6 kilometres an hour is close to the maximum speed of around 7 kilometres an hour for a regular housefly, so the poor creature is going to have to fly close to their top speed for an hour without tiring or slowing down. In fact, studies have shown that flies can fly for 5 or 6 hours without stopping, so this might not be an unreasonable assumption even in the real world. Now we've made a whole series of observations about how the problem was basically untenable, let's make our assumptions and go ahead and find the answer. I'm guessing that quite a few viewers will already have encountered this problem before and will be aware that there's a difficult and an easy way to approach the problem. The easy way is to ignore the fly for the moment. Concentrate on the horses. They start 6 kilometres apart, travel towards each other, both at 3 kilometres an hour, so they'll meet in the middle, both having travelled 3 kilometres. Travelling 3 kilometres at 3 kilometres an hour takes an hour. Meanwhile, the fly was travelling back and forth between their noses at a constant 6 kilometres an hour for the hour. It would have travelled 6 kilometres. I want to spend a bit of time on the harder solution though, because it's a bit more interesting. If you think about the story from the fly's point of view, it sets off along a 6-kilometre track and encounters a horse's nose along the way. Then it turns around and flies back the way it came. It travels at 6 kilometres an hour and soon encounters the same horse's nose that it started on, although the horse has moved since the start. And it turns around again and pretty soon encounters the second horse again, and so on and so on. We end up with a sequence of journeys back and forth, each one getting shorter and shorter until there's a stramash in the middle resulting in a squashed fly. Let's work out how far the fly travels on each leg of its journey. Let df be the displacement of the fly from its starting point in kilometres. Let t be the number of hours that pass, and let dh2 be the displacement of the second horse from the starting point of the first horse and fly in kilometres. So df is equal to 6 times t, and dh2 is equal to 6 minus 3 times t. Every 1 hour, the fly travels 6 kilometres, and the second horse starts with a 6 kilometre displacement and reduces this by 3 kilometres every hour. Now, these equations are simultaneously true, and the fly encounters horse number 2 when their displacement from the start is the same. So df is equal to dh2. Then 6t is equal to 6 minus 3t. Adding 3 to both sides means that 9t is equal to 6. And then dividing both sides by 9, we find that t is equal to 2/3. This means that the fly bumps into the nose of the second horse after 2/3 of an hour, or 40 minutes. Substituting the time t equals 2/3 back into our first equation tells us that the fly travelled 4 kilometres to encounter the second horse for the first time. Now the fly turns around instantaneously and flies back to the first horse, but remember that both horses travelled 2 kilometres each in that 40 minutes that the fly was flying between them, and they carry on moving as the fly is flying back to the first horse. And following the calculations through, we see that the fly travelled 4/3 or 1 1/3 of a kilometre from the second horse's nose back to the first horse's nose on that second leg of the journey. We then discover that for the third leg it travelled 4/9 of a kilometre, for the next leg of the journey it was 4/27, then 4/81, and so on. If we look at the series of distances that the fly travels from nose to nose, the terms make a geometric progression, and the first term of that would be 4 with a common ratio of 1/3. It means that each subsequent leg is 1/3 the distance of the previous leg, and now we just need to add up all those terms. Now, the formula that tells us the sum of n terms of a geometric progression is the sum of n terms is equal to a, the first term, times 1 minus r, the common ratio, to the power of n, all over 1 minus r. So, for example, by the time the fly has flown back and forth between the horses 14 times, it's travelled a total of 5.999999875 kilometres. And in fact, at that point, the horse's noses are just 2.5 millimetres apart. In the real world, the fly would now be squashed. But in math world, we don't let minor details like that worry us. We carry on summing an infinite number of terms, and we find out that if we do that, the fly would travel 6 kilometres exactly. So, in conclusion, if we go along with the math world assumptions, we'd say that the fly travelled 6 kilometres. If we made a few concessions to reality, we'd say it flew a couple of millimetres shy of 6 kilometres, at which time it was squashed. If we tried to recreate the situation in the real world, we'd probably say that it's a ridiculous problem and you couldn't recreate it. When you subscribe to our channel, remember to click the bell to ensure you get notifications about our new videos. And for more mathematics content, why not follow the link in the description below to nagwa.com.